we have to think about vectors and matrices, but let's start with vectors. It's the same thing as numbers. They're things. And just like with numbers, we can operate on numbers, right? We can operate on vectors no different than how we operate on numbers. We'll get into some of those operations in a moment, but there is a fundamental operation between two vectors. And that fundamental operation is what is referred to as the inner product. And the idea is, if given two vectors, x and y, can I somehow convert the two vectors into a single number from the real numbers? The answer is yes. So basically, I'm operating on vectors of numbers by doing something to them and converting them into just one single number. And that one single number represents something interesting about the vectors, which we're not really going to get too far into. But the basic idea is to algebraically take the two vectors and convert them into a number. Now, the one condition that needs to hold true is that the vectors need to be the same size, meaning they need to have the same number of elements. If the vectors are different sizes, we can't do this operation. But if we have two vectors of the same size, suppose we have one vector, both vectors are of size, let's say, n, okay? The inner product is defined between the two vectors. You know what, let me take a step back because I'm saying vectors, but I'm not being clear here. Usually when we say vectors, the authors, whatever book you're reading, usually assume something about the vectors. They're either row or column vectors. And when they put a T on the vector, they're emphasizing they're converting it from the defaults to something else. So in this instance, we're going to just assume that anytime I say vector, we're going to assume that that's just a column vector. So if I say let x and y be vectors, we're assuming those are column vectors. Now, if I have two column vectors, the idea in this type of algebra is I can't put together two column vectors. It's kind of strange. That is, I can't take two column vectors and convert it into a number in the real numbers. But what I can do is take the transpose of one of them and multiply that against the column vector. So when I do the T, this now turns into a row vector, where we have only one row, but we have n entries. And the column vector here has a total of n entries and one column. The way that we define the inner products between the two vectors, okay, as you can see, the two ends here are going to cancel, and we're left with a 1-by-1 matrix, which is usually assumed to be equivalent to a number. We can convert them to numbers by multiplying the elements and adding them all together. So the way that we represent this is x1, x2, up to xn. And then we have our column of y's, y1, y2, yn. And again, what we do is we multiply this times this times this, that times that. And we add them together. So we get x1 times y1 plus x2 times y2 plus xn times yn. That's not m. That's just n. And that, by definition, is an inner product between two vectors. So, for example, if I have the vectors 2 and 3 and 4 and 5, then to find the inner product of these two vectors, what I end up having is the 2, 3 in row notation times the 4, 5 in column notation is equal to 4 times 2 plus 3, 5 times 3, which of course is 8 plus 15, which of course is 23. So the inner product of these two vectors is 23. If you do this for a bigger set of bigger vectors, 1, 1, 1, and let's say 2, 3, 4. The inner product of these two vectors is the row vector and column, which is 2 times 1, which is 2, plus 3 times 1, which is 3, plus 4 times 1, which is 4, which gives us 9. So I don't know if you've picked up on this yet, but you can actually represent linear equations in terms of inner products. So if we have, let's say, 2x1 plus 3x2 minus 4x3 is equal to 2, then you'll notice that I have a whole bunch of coefficients, and then I have a whole bunch of variables. So if I let the vector A equal 2, 3, and minus 4, and I let the vector x represent x1, x2, x3, then you'll notice that this is nothing more than the inner product of A and X, because if you take the inner product of A and X, you take the transpose of A, and you get 2, 3 minus 4. You leave the X alone, and you'll notice you get 2 times x1 plus 3 times x2 plus minus 4 times x3. So what does the inner product allow us to do? It allows us to shorten our equations down, because now I can say, if I let these A represent this and X represent this, then I have A transpose. Don't forget the transpose. I can't emphasize this enough. Students who start linear algebra education always mess this up. Don't forget the transpose. In inner products, the first vector is always a row vector, and the second vector is always a column vector. And if we are assuming that all of our vectors are in rows, if I take A times X, that makes no sense because they're both column vectors. So we need to apply the transpose operation to convert it to row so that life is good. Because if you were to assume that this is a column vector, then you have a 3 by 1 matrix, and you have a 3 by 1 matrix here. And what we'll soon find out is these are what are called incompatible matrices, because these two numbers are not equal to each other. That requirement in any operation of matrices always needs to be true. So no, this is not a pet peeve of mine, so to speak. This just simply is a matter of right or wrong. We're assuming they're all column vectors. We therefore need to put a transpose on the front. If we had assumed they are all row vectors, we would put the transpose on the second quantity, but we are not assuming that. However, some textbooks will. So always make sure when you read a textbook or a paper, you try and figure out, usually the authors are pretty good about telling you what their notation actually represents, because it's a matter of style. whether or not they use column or row vectors. However, I will say overwhelmingly, authors assume column vectors, not row vectors. So anyway, short of that small tangent, we have the, we can represent this equation as the transpose of the vector A and the inner product of that with the vector X, and that's just equal to 2. If you haven't followed that, right, just write it out like that, because you know that this times this is this, plus this times this is this, this times this is this, add it all together, and you get that same equation. So this here is the same thing as writing A T dot X. So that's an inner product. Inner products give us information about the vectors geometrically. It allows us to understand the angles between the two vectors geometrically, although we're not going to get that far into this. However, what the inner product also does is allow us to shorten down a lot of our notation here, because instead of writing out these equations, I can just write them in a very compact, elegant form like that. And you're going to see a lot of that. One last thing to note. There's a lot of different ways to represent the inner product. You'll sometimes see this. Oops. If I have two column vectors, A and B, you'll sometimes see this. This is another way of writing the transpose. And I know this gets very confusing because I had mentioned all the way back in set theory that that's another way of writing the complement of a set. And here's what gets even more confusing. Some authors will write a capital letter for a matrix, and then you have the transpose of that. Well, is this the complement of a set, or is that the transpose of a matrix? The answer depends on the context, of course. But anyway, this is one way of writing the dot, or the inner product, which is also referred to, by the way, as the dot product. Sometimes you'll see it represented like this. Sometimes you'll see it represented like this without the transpose, okay? Sometimes you'll see it represented like this. Sometimes you'll see it represented like this. And then, of course, as I've mentioned before, sometimes you'll see it represented like this, or like this. Authors have their own styles, and usually in a publication, they'll tell you exactly what they mean or what they're using to refer to as the dot. But don't be afraid, because at the end of the day, this is very simple stuff. You're just taking the elements in position I, okay, starting at position 1, sometimes 0, but we'll do 1, going up to position n, and you're just multiplying the element in position I for the first vector times the element in position I of the second vector. Okay, again, two vectors. You're just matching the elements, element by element, multiplying them, and then adding them all together to get your dot product. So those are the concepts of the inner or dot product. Let me make one very last thing very, very clear, okay? Taking the dot product, okay, this is not the same thing as doing this, assuming both of them are column vectors. If you think about it, this is a 1 by n matrix. This is an n by 1 matrix, and that's good because the two here are compatible. Again, we'll get more into that in a moment. Here, this is assumed to be a column matrix, so this is just 1 by, I'm sorry, no. This is n by 1, okay? And this is because this was a column, now it's a row, this is 1 by n. Notice the result here is a 1 by 1 matrix. The result here is an n by n matrix, because the inners always cancel out when we do that stuff. And again, I'll get into that more. But I want to illustrate ahead of time that this is not true, okay? I can't take a transpose of a column vector and multiply it in the same way as this. This is what we refer to as the inner product. This is what we refer to as the outer product of two vectors. The inner product converts the vector into the two vectors into a number. The outer product converts the two vectors into a matrix. And that is something entirely different, which I'm not going to get into at this moment in time until we get through a few other properties of our matrices.